real coaxial cable found in a physics lab or connected to a cable TV. Okay, that's what it is. Has an inner conducting solid cylinder radius A. This is the wire. And an outer conducting cylindrical shell, inner radius B. It's physically easy to set up a fixed given potential difference between the inner and the outer conductor, keeping the entire coax neutral. Okay, assuming infinite cylinders, find the capacitance of the system per unit length. So per meters, because the cylinder goes to infinity. Express your answers in terms of A, B, C, A, B, and the constants of nature. Okay, so basically we need to find the capacitance for the system, right?
Yeah.
You read? Yeah. So if you draw a figure, basically what this is, it's you know, a cylinder like this. Okay, and then this is the inner one, and this is the outer one, right? And this goes to infinity, and let's say that the radius here is A, and the radius here is B. Okay, and this is all kept this is all grounded, so it's neutral, right? So that means if there's a lambda charge on this, there's a minus lambda charge on this, so that the sum would add up to 0. So if we take a front view of this thing, yeah, we're gonna get this is A with lambda here, and this is B. This is a front view of what we're looking at, and this is B, and there's a minus lambda here, right? And this goes into and out of the page infinitely.
Right.
And so the question for A is find the capacitance, and we know that the capacitance is the ratio between charge and voltage, right? That's what it is, and we are trying to find the capacitance per unit length. So the best way to tackle this problem is to actually figure out the potential, and then you know, just we take the ratio between the charge and the potential. Now, to find the potential, we have to know the electric fields, but that's relatively easy because we know if we go for R greater than B, right here, we know that if you take a Gaussian surface around this whole thing, right, we know that Q enclosed will be 0 because it's neutral, and therefore the electric field according to Gauss's law will be 0 for R greater than B. And with the same exact reasoning, if you were to take a Gaussian surface here, right, the radius small r, so this is where R is less than A, right? Q enclosed is also 0. There's no charge on this gold Gaussian surface.
Yeah, it all
and so E is 0. So there's two regions where E is 0, here and here. And the only place we have electric field will be here, will be in the middle, right? Because here you're gonna enclose charge. If you take a Gaussian surface here, sorry, not here, in between, A and B, so this is where R, or let's call it S, since we are dealing with a cylinder. If S is between A and B, right, you will get an electric field, because now Q enclosed is not zero. So basically what I'm doing is, to find the capacitance, I have to find the potential. To find the potential, you have to find the electric fields, because you have to integrate the electric field to get the potential. And once you have the potential as a function of charge, you can take the ratio and find the capacitance. Right? So here Q enclosed will just be lambda, this is charge per unit length, times the length. If this is my L here, if I take a piece of this cylinder, this is my L. Right? And so now I can apply Gauss's law like I did above. EDA is equal to Q enclosed over epsilon. And again, this is a dot product between the two vectors, but because of symmetry on a cylinder, right, dA vector is the vector perpendicular to the surface, right, but E is also perpendicular to the surface, so those two point in the same direction, so E can come outside the integral, and this simply becomes EA equal Q enclosed over epsilon, right? And the area of that piece of a cylinder, right, is just 2 pi s, because the radius of my Gaussian surface here is s, 2 pi SL equal Q enclosed, which is lambda L divided by epsilon. And now I could find my electric field to be, the L's cancel, it's independent of the length of the cylinder, becomes lambda over 2 pi S epsilon. And that's in the S direction if I make this a vector. So this is the electric field when S is in between A and B. And the minute I have my electric field, I can find my potential. My potential will be negative the integral from a reference to all the way to the center, right, to 0, of E dot dl, and dl in this case is just ds. Right, so this can go from, so where's my reference? I can't set my reference at infinity here because this is an infinite cylinder. However, I could set my reference on the surface where this is grounded, right? It's 0 on the surface. Neutral, meaning delta V here is 0. So I could take this integral from A to B, sorry, from B to A, right? EDL or EDS minus, so I'm just splitting up the integral from A to 0 EDS. And I know that here I don't have any electric field. This guy is 0, but I do have an electric field between A and B, so I plug the E that I found in here, right? So then V is minus integral from B to A. This is lambda over 2 pi epsilon 1 over S ds. And this whole, you understand what I'm saying?
Yeah, I think so.
And so this whole thing is a constant. It can come out. So this is minus lambda over 2 pi epsilon. Integral of 1 over S ds will be L and S from B to A, right? Or if I want, I could switch the bounds of the integral at the cost of this minus sign here. So I can make it A to B. And obviously this becomes lambda over 2 pi epsilon ln B minus ln A, which would be ln B over A. Right? Now, we know that the capacitance is Q over V, right? So I need to get Q in this equation, and that's easy. I could just replace lambda by Q, QL, right? So then this becomes V equal QL over 2 pi epsilon L and B over A. And now I could just take the ratio. The capacitance is Q over V. So I could figure out what the ratio is from here. So C equals Q over V, right? And the ratio here would be Q. So what multiplies Q goes here. So this is L, right? This is gonna be 2 pi epsilon ln wait, sorry, I messed up. Lambda is Q over L, not Q times L. Q over L, so the L goes here. Okay, and now just make the ratio. So this is 2 pi epsilon L times ln B over A divided by no, ln B over A is on the bottom, yeah? Having some algebra issues here. So this is ln B over A. And since it's asking for capacitance per unit length, I could divide both sides by L, and my final answer will be capacitance per unit length will be 2 pi epsilon over ln B over A. So this would be the capacitance per unit length of that conductor. Making sense what I did or no? You could have started with the charge without involving lambda if you want. you'd still got the same answer. I just stuck in lambda, and then at the end I went back and I replaced it by Q over L.
Right.
But basically the strategy on these questions is to always find the electric fields in the regions of interest. From there you could find your potential. From the potential, because there's going to be charge in the potential, you can take the ratio of the charge per voltage,
Yeah.
and that would be the capacitance.
Right.
Okay, I'll let you
Oh, wait a minute.
try it out. Part B, it says find the energy stored per unit length inside the capacitor. There are many ways to do this, but he wants you in this specific question to integrate the energy density that is actually stored in the electric field itself. Right? So and then we could check the answer using the algebraic formula 1/2 C delta V squared. In other words, if you were to take the energy density which is epsilon over 2 the magnitude of E squared. This is how much energy you have per unit volume. And if you actually integrate this over the volume d tau, right, you would get the work or the energy. This is and by the way, this formula, the way it's derived, you are actually integrating over all space. Why? Because technically this is not the complete formula. In addition to this component, there's another component where you have the integral over a surface area, the integral of V times E over the surface area, but you could extend the volume of integration because anyways the electric field there is 0, and as you extend the surface area, that component goes to 0 and this component picks up the slack. You understand what and we've calculated in A the electric fields everywhere, so you should be able to figure out what this is.
Alright. Yeah. Okay. So that would be.
So yeah, we found the electric field everywhere. All you have to do now is integrate it. There's basically 3 regions. There's where S is greater than B, S is in between A and B, and S is less than A, right? So that means we go from infinity to B, that's the outer radius of the electric field there, times d tau squared, plus from B to A of the let's call them E1, E2 squared d tau, plus B to 0, right? Because that will be the entire electric field, this accounts for the entire energy stored in all space in the entire electric field. Now we already said if you were to take a Gaussian surface around the entire conductor per unit length, Q enclosed will be 0. We already said E equals 0 here. So E1, this one here is E1, right? This was E3, and this here was E2. So we have all of them, yeah? So those 2 terms go away. There's no electric field here, right? So this guy is 0, and this guy is 0. Sorry, this is supposed to be A, not B. Inside the inner surface, because the charge is all on the surface.
Right.
And so that's the only electric field we have. So you just have to integrate that from B to A. What was E was, we found it here, right? Lambda over 2 pi s epsilon, lambda over 2 pi epsilon squared. This is all a constant, it can come outside, and then we have 1 over s squared ds. And so this will be epsilon over 2 lambda squared over 4 pi squared epsilon squared, and the integral of 1 over s squared is minus 1 over s from B to A. And now it's just, a matter of evaluating. So 1 epsilon cancels. Now lambda, we said, is the charge divided by L. So this is going to be Q squared over L squared, right? And here we have epsilon over 2, because wait, no, 1 epsilon cancels out, and we get so this is lambda squared, epsilon goes away, we get 8 pi squared epsilon, and this is 1 over A minus 1 over B, but we have a minus sign, so this becomes 1 over B minus 1 over A. And if you want this, the question said it wants it per unit length. Now we could divide here by L, right? Because it said find the energy stored per unit length. So if I divide by L, right? So technically this is the energy density. This is the energy stored in the capacitor. Okay. Now let's check. We know in general that W is equal 1/2 C delta V squared, right? So 1/2, we know the capacitance. The capacitance is, where did we find it? Here. It's 2 pi epsilon L
over ln
2 pi epsilon L over ln B over A. Oh wait, I was wondering, we have a mistake here. It's not ds, it's d tau.
What was tau, by the way?
The volume element.
Is that volume and cylindrical?
I was wondering why this is not making sense to me.
Tau, is that volume and cylindrical coordinates in this book?
Yes.
Okay.
Not necessarily cylindrical coordinates, whatever the shape is. In this case, since we have a cylinder,
right.
it's better to do it in cylindrical.
Right, because V is potential. Right.
In cylindrical coordinates.
Yeah, Yeah, I forgot because V is potential. So yeah, that's why it's out. Then what do they use in the relativity chapter though? And they have D, or I don't know if they. That's only for. Yeah, they
Same
must
thing.
use something. Well, they use for S squared minus. T
So
squared minus
this
R
will
squared.
be, you know what, so you're integrating over the surface, so this is going to be s squared, right? Wait 1 second. This is going to be s squared in cylindrical coordinates, because you're taking an elemental volume,
Yeah.
right? And you're gonna multiply by ds, right? S squared, no, sorry, not s squared, sds. It's cylindrical coordinates, so you're taking a portion of the cylinder, like let's say this. So you're going so this here will be this is going inside, so this will be s d phi, because you're going around. So actually let me make it like this. So this will be s d phi, right? And then you have the theta, so you have then you have s d phi times ds, because the length of this is ds, times d theta. Okay, and so this is a triple integral, and ds is going from b to a, d phi is going 0 to 2 pi. Wait, there's no d theta, there's no theta in the cylinder, right? Hold on 1 second, let me think about this. Okay, this is the cylinder. Okay, and you're actually taking a piece here, right? So technically this is ds, right? And you're measuring from the center, so the width is ds, the wait, no, this is the cylinder. You're going, let's say that this is the axis, okay, and you are, and let's say this is your cylinder here. Okay, so technically you are taking a piece of this cylinder here, okay, and you're gonna try, so this axis technically goes in the middle, not like I drew it, it's here. Okay, you are and let's say your center is here, right? So you are going, what's the volume of this cylindrical element? It's length times width times height.
Yeah.
Okay, well, the height is S. Let me move this down here. It's taking forever to move. Okay, so this is the elemental piece. So the height, clearly how far you are, will be ds. Okay, this piece here is ds. I don't know why this is giving me a hard time.
Is it getting hot? Is there something blocking the vent?
I don't know. It's just taking a long time to process. It's not.
My laptop actually just shut off like out of nowhere the other day. Like, thankfully everything was still there. Like it like rebooted to it like reset itself or something. And thankfully it didn't. As far as I know, I haven't lost any data, but like it was weird. Like it just like I was using it and just shut off.
Yeah. Hold on 1 second. I want to see something here. I just want to confirm. I don't like this picture is not doing it. Second. Does she have the cylindrical coordinates here? Probably not. I mean, I know what the answer is. I just want to show you like how it's done. I think my flaw is how to draw this. Honestly, I know what each one will get. Okay, here we go. So if this, let's say that this is your axis. Okay. And let's take piece of the cylinder. Okay. Something like this. Right, so let's say that this is piece of the cylinder. Technically this is a little bit curved here, right? So this, look, this is the z-axis here. Okay, so what's the volume of this piece? Well, you're going dz in the height. Okay, the angle, like the angle here would be d theta, right? Or d phi. Let's use phi. So because you're integrating around the entire cylinder, okay, and so this piece here, remember the distance from here to here is s. So this piece here would be s d phi, right? Because this is really an elemental angle. So okay, so we have the height of the piece, we have the width, and this length here from here to here would be ds. And so the volume of this element would be length times width times height, so it's gonna be s d phi times dz times ds. So it's going to become s ds d phi dz. And s goes from b to a, phi goes from 0 to 2 pi, because, you know, to encircle the full cylinder you go around 2 pi. And dz, that's the length of the cylinder, because that's how long we're going. So this is 0 to L, because we took an L piece of the cylinder. Doesn't matter because it's going to be per unit length, but for now let's just do it appropriately. Okay, so this is cylindrical coordinates here. I wanted to show you, so because this is always useful, you can always do it and see like how it's done. Cylindrical coordinates. Okay, so if we integrate, you know, this is a straightforward integral. W, this will be epsilon over 2. This whole thing is a constant. It just comes out. Lambda squared over 4 pi squared epsilon squared. 1s cancels. The integral of 1s over s will be ln s from b to a. Integral of d phi from 0 to 2 pi clearly will be 2 pi. And integral of dz will be z from 0 to L, so that's going to get you L. And so now, just simplifying, this will be epsilon over 2. We have a pi cancelling here and a 2 cancelling. So we're left with, let's see here, 8 and 2, so this is 4. 1 epsilon cancels out, we get an epsilon left and a pi left, so 4 pi epsilon, right? We have lambda squared. Let's just write for lambda squared what it is. That's q squared divided by L squared. We have ln b minus ln a, which would be ln b over a, and we have L. And so if we simplify, 1L cancels out, and we get the energy stored in the field to be, 1 epsilon also cancels. There's no more epsilon here. So we get q squared over 4 pi epsilon, 1L cancels, L, ln b over a. Okay, this would be the energy stored in the field. Let's verify. So let's use the other algebraic formula. We know that work is 1/2 c delta v squared. We already found the capacitance, so let's plug it in. Of course, we should get the same answer if this is consistent. The capacitance was 2 pi epsilon L over ln b over a. Oh, by the way, I made a mistake here. This is ln a over b because it's ln a minus ln b. So this is a over b. Okay, so back to here. So this is the capacitance was 2 pi epsilon. Oops. 2 pi epsilon over closing on me. Okay, so 2 pi epsilon over what was it times L and B over A times L over L and B over A, right? And what was the potential squared? So this is Q over 2 pi epsilon L Q squared over 2 pi, so this becomes 4 pi squared epsilon squared L squared, right? Because we're squaring each term, and epsilon, and then L N B over A. Ln B over A squared. Okay, and just simplify, so we get the work is equal to the 2 cancels out, pi cancels out, epsilon cancels out, L cancels out, so indeed we get Q squared over, we have 8, 2, so 4 pi epsilon L, right? And then one of these cancels out, so we get ln B over A. So because you're squaring it, because you know ln, look, ln, anyways you have to take the absolute value of the capacitance, but ln A over B is the same thing as ln B over A to the minus 1, right? If you switch them, and this minus sign comes down, so you get ln B over A, and when you square it, the minus sign goes away, so it doesn't really matter. So the point here is yes, we do get A over B, okay, but then when I apply this, I could equally likely here switch these, right? So so I would get so yeah, I could make this the capacitance turned out to be the capacitance was ln B over A. Okay, so this is correct, there's no problem here. But then when you square the delta V, like I explained to you, because the minus sign doesn't matter, you could make this A over B, right? And there's a minus sign here, which doesn't really matter. True?
Right.
And this is just ln A over B here, and one of them cancels out, and we get one of those ln's goes away, and we get ln A over B which is the same result we got from integrating the electric field over all space. So this confirms that you have the right answer. You could, if you want to find this per unit length, you could divide by L, and Q squared over L squared would just be lambda squared, because you're dividing here by L as well. So you get lambda squared over 4 pi epsilon ln A over B. Now, A is less than B, correct? Because B is a greater radius. So this here will be a negative number. So anyways, you have to take the absolute value of this. Because this will be less than 1. So we're supposed to do the absolute value of this, which would be the same as if you had B over A, but without the absolute value. You know what I mean? But this is how you find the energy stored in the conductor.